and thank you for the invitation. So this works, right? Let's do this. Okay. Okay, so yeah, I'm going to be talking about non-contractible periodic orbits. There will be a lot of things that I'm going to use that Victor mentioned or will be mentioning. So the plan, what I want to do first, I want to introduce the question, talk a little bit about it, some of the results, and in the first approximation, we will look at the simplest case of the theorem, and then we'll try to prove it. And then in the next lecture, I want to look into a little bit more technical version of the theorem. That what do we need to, new things that we need to introduce to look into a little more technical version. Okay, so we have, here's the setting. So we have a closed symplectic manifold. And Hamiltonians, which I will always assume to be time-dependent non-periodic. And again, as Victor introduced, this is the time-dependent flow of H. Flow of H or the vector field XH, and we have the Hamiltonian diffeomorphism, which is determinant of this map. So PH1, or oftentimes I'll probably write just P. Hamiltonian diffeomorphism. Okay, so the flow, again, as Victor said, this is a family of diffeomorphisms starting with identity. Okay, so in the morning, Victor introduced the problem of looking at simple periodic orbits of this Hamiltonian flow. And by periodic orbits, we understand basically maybe I can write it this way. I'm not going to use this notation much, but maybe I just want to for now have this written. So I look at the fixed points of the iterations of the Hamiltonian diffeomorphism and just take the union of all of them. Again, you should think of these periodic orbits as only the ones with integer period of the flow. Okay, so most often one looks at one looks at the contractible periodic orbits in this case, but today we are going to look at, in my lectures, we're going to look at non-contractible case. Okay, so studying non-contractible period. Okay, so, well, with this, let me go ahead and introduce some notation here. So, pi 1 of m tilde, which will be all over the place. This is the set of homotopy classes. So this is the set of the homotopy classes of free loops on M. So these are the conjugacy classes of conjugacy classes in the fundamental group, basically, right? So, right, it's not a nice object. Of course, it's not a group. Like this. Okay, so now I'll try to stick to the following notation. So there will be periodic orbits all over the place. So I'll try to, for a loop X, so this is a map from S1 to M, I'll try to stick to this bracket as elements in pi 1 tilde, and when I use the square bracket, this would be the homology class torsion. Integer homology classes torsion. Okay. Maybe not to be pedantic, but just to make sure everything is clear. For instance, if we, take a free homotopy class here, one can of course look at its homology class like this. Okay, so now this would be, if I do something like that, then elements here will come from actually all zeta i's which have the same homotopy, the same homology class. Okay, so this comes from all zeta I in pi 1 tilde. Joker is the three homotopy classes of groups in this homology class. Okay, so now further notation. So let me introduce this notation P sub k h. I will use h or sometimes ph here, or ph in place of h or p. Here I can put actually a collection of homotopy classes. This would be fine. Let me just stick to one for the time being. So zeta is a free homotopy class here. So these are the k-periodic orbits. In this class. Okay. Again, sometimes I can put a homology class here. You should think of then all the orbits coming from, contributions from all the homotopy classes contributing to the homology class here, if I put it like that. So now, what we want is, we want to study non-contractible orbits. So we want zeta to be a non-contractible class. So what I want is, this is not identity. And the question that I want to sort of study, ask, is if there are any non-contractible orbits. So in other words, can we say anything about this set? Periodic orbits. You need something, of course. For example, one thing we may need is that the homology is non-zero. There may be, if there are, can we say that there is an orbit in a given class? In a given zeta, let's say. Okay. This is one of those things which we know very little about somehow. This kind of question, and especially, a little bit later I'll get to this closed manifolds versus open manifolds, etc. But basically, very little is known about general study of non-contractible orbits. But of course, we will be easily answer this question in a second. And the answer is no. Okay. So maybe I should have can write it here. Answer is no because, you know, take a surface, for instance, of genus at least one, and take a small function on it, small bump function on it. It has no contractible periodic orbits whatsoever. Basically, likewise, you want it to be small support. Likewise, a self-indexing Morse function also, which it won't have any contractibility, it won't have any non-contractible periodic orbits. Okay, so the answer is no, again, as the simple examples show. Moreover, from the Floer theoretic perspective, we know that Floer homology, let me write it this way. Again, I'll try to say a few words about this object too later on when we get to proving something. So here what I mean is that this would be the homology of the complex generated by one periodic orbits of H, which come from this homotopic class, basically. So it's, of course, the well-known thing. Okay, so now this object is 0. M is again closed if zeta is not 1. For the simple reason that, again, if you take a C2 small autonomous function, all its critical, all its periodic orbits are the critical points, all of which are contractible, and so this is going to be 0, basically. Okay, so the entire complex, non-contractible complex can be 0. Basically, there is absolutely no reason to expect anything here. The existence of a non-contractible orbit. Nonetheless, I want to say one more thing here, which is that, as I said, there are examples like the small bump function. However, there is no like a generic Hamiltonian diffeomorphism with isolated periodic orbits, which doesn't have a non-contractible periodic orbit, basically. Again, assuming that H1 is non-zero. So in fact, here is a conjecture. Okay. So this is actually our conjecture. And we think that if pi1 or H1 is rich enough or large enough, again, for example, a surface of surfaces of positive genus, then a C infinity generic phi has a non-contractible periodic orbit. Okay. So, again, as I said, you can think of a surface like that. This is actually known for T2. It's been proved recently, well, not so recently, maybe by now. It's a 2015 paper by Le Calves and but nothing else at the moment is known. Let me say, there was another question in the picture, which was, yeah, I also raised the question of existence of non-contractible orbits in a given homotopic class, as to whether or not you can specify anything here in the presence of non-contractible orbits, and the answer to this is also no. basically. So, and for example, just think of something like that. So maybe I will write it this way. Cannot prescribe different homotopicals. So think of something like that on the torus, right? Basically. Okay, so the conclusion of this little story is basically that one has to assume something. So one has to assume something on the manifolds and or possibly on the Hamiltonian diffeomorphism Hamiltonian in order to expect anything you know, about the non-contractible existence of non-contractible periodic orbits. Okay, so let me write the first theorem here, which is, as I said, the one we will try to prove hopefully today. The least technical theorem here. It's partly the paper I wrote in 13 and then a version which works for bigger classes of manifolds we wrote with Ginsburg. So here's the theorem. So phi h or phi and omega a Hamiltonian diffeomorphism. I need to tell you more importantly what kind of M's I'm working with. So here, assume that omega is a toroidal. This means that the integral of the symplectic form vanishes over all toroidal classes. So let me write it this way. So we star omega is 0 over T2 for all V. And phi has I'm continuing. So this is the setting of the manifold. Assume that phi h has an isolated periodic orbit x with a non-zero local Floer homology. Again, I will say a few words about this a bit later, and I'm sure Victor will talk about this too, maybe tomorrow. So with non-zero local Floer homology, for now, actually, the good way to think about it is just an example of an isolated orbit with non-zero local Floer homology is a non-degenerate orbit. Just think about non-degenerate. This is example. Okay. So the linearization of the doesn't have one as an eigenvalue. Okay, so such that I do want to do something, and I want to actually write here. So I think we can erase this, and then I will leave the theorem here. Okay, so one. I assume that the corresponding homology class, H1 or torsion again, is non-zero. H1 and torsion. And two, that the number of one-periodic orbits of phi in this homology class is finite. Okay. So now the assertion is that for every sufficiently large prime P, the diffeomorphism, the Hamiltonian diffeomorphism phi has a simple periodic orbit. This orbit is in iterated classes. So if the homotopy class of my orbit, if I try to denote it by bracket x, this will be in class x to the p. So I will actually a bit later start using this notation, but it means that in the classes of the iterations of the given orbit, so I'll write it this way. This is in I1 theta. And with period P or P prime, where P prime is the first prime that comes after P. So first prime after P. Okay. So there is a moreover part to this. If it happens that pi 1 of m is hyperbolic and torsion free, then actually in place of this assumptions 1 and 2, I can simply assume that the homotopy class of the orbit is non-trivial. So it suffices to assume that this is not equal to 1 in place of I and 2I. Okay. Are there any questions about the statement of the theorem? It's a little bit lengthy. Well, you will understand in due time. It's a little early to say that, but there will be, we will need to work in the proof, and then we will see that how big it will be chosen. Other questions? Okay, so this is the theorem. So basically, in short, to take home, it says that no, we don't have to have non-contractible periodic orbits, but if you have one, it basically generates infinitely many. This is, in short, this is what this theorem says. And there will be, as I said, maybe this is a continuation. The first thing I want to say, maybe it's under remarks, etc. Number 0 is that, as we will see, a version of this theorem holds under a weaker condition that symplectic manifold is toroidally monotone, or in the presence of a non-contractible hyperbolic orbit. So again, we will see that too later. Or maybe now I'm just going to write S for toroidally monotone. And in the presence of a non-contractible hyperbolic orbit. Okay. Now, one is important. very recently, the version of this theorem was proved by Orita. The same result for manifolds which are T2n times n toroidal symplectic manifold. Let me just write this. So this is a very recent preprint. Okay. So the same result holds for m2 and omega. So here, his symplectic manifold is T2n cross another closed symplectic manifold. We equipped with the symplectic form, the standard one on the torus, and an atoroidal one on n. So this one is atoroidal. Okay, so in particular, this theorem holds for T2n. By taking n to be a point for T2n. So this is important. This is a case that's not covered by this, obviously, and it was not covered by any of this either. Obviously, torus is not a toroidal monotone manifold or atoroidal manifold. So I will try to say a few words about this as well, but it will be more appropriate to talk about it after we maybe go through the proof of this. So this is a very recent result. Maybe just one more thing. So when I say the theorem holds, I am only talking about the parts before the moreover part here. After the moreover part doesn't really make sense here because your pi 1 is never going to be hyperbolic in this case because of this torus, basically. Okay? So up to the moreover part. Okay, so next, a few more remarks. So what kinds of manifolds are we talking about here? So maybe it makes sense to say something about this. Well, we want atoroidal. Anything atoroidal should be aspherical, obviously. So we are not talking about our, standard CPNs and things like that. So surfaces of higher genus. So, and then more generally, we are talking about closed scalar manifolds with negative curvature. Negative sectional curvature. So more generally, one should think about the case of an hyperbolic pi 1 and pi 2, 0. This kind of manifolds fits in the definitely in the bill. Again, surfaces are in this category. Now you may think that actually, well, everything we know actually fits into this hyperbolic pi 1 case, but there are actually other examples. It turns out that so I'm not going to be able to tell you anything explicit, but there are some other manifolds which are atoroidal actually, I think symplectically toroidal. I think C1 is 0, 2 in that case, without the pi1 being hyperbolic. These are due to, there are two papers by Rumbauer and Kochik, and also there is the work of basically constructions of such things, basically. So there are sort of examples, there would be good amount of examples where these theorems hold. Okay, next. Hamiltonian diffeomorphisms. We'll say a few words about those two. So we have here a Hamiltonian diffeomorphism, which is a non-degenerate orbit or a non-contractible orbit with this property. So Hamiltonian diffuse. Which fits the bill here. So here's a result of Botterill, and she says that if you give me any pre-homotopy class, there is actually a Hamiltonian diffeomorphism which has a non-degenerate one periodic orbit in this class and finitely many periodic orbits in the corresponding homology class. So let me write this. So there exists a pH with a non-degenerate one periodic orbit in beta, and P, I believe it's like that, is finite. So this is So furthermore, under the conditions of this theorem or the other theorem that I haven't written down yet, these guys actually, in the manifolds where these conditions hold, such diffeomorphism are open as infinitely open set of Ham, basically among the Hamiltonian group of Hamiltonian diffeomorphisms. So there are Hamiltonian diffeomorphisms, plenty of that this thing applies to. So now I want to, so maybe let's leave it here, on to that board. Say a few words about some other works. Of course, there were other works which, people studied non-contractible periodic orbits in the context of Floer theory. So let's look into this a little bit. Okay. So again, focusing on the context of symplectic topology using Floer theoretic methods, non-contractible orbits were studied by various people, like in the paper of Biram Poltarovich and Solomon, going back to 2002, something like that. Gatien Lalonde. Which was generalized by Eugene Lee. And then Weber and Solomon, this was also, I think, generalizing some ideas from BPS, Biram Poltarovich, Solomon. Nietzsche studied them. Hopefully I'm not forgetting anybody. So, studied non-contractible periodic orbits. However, with one difference from our case is that all of them concern open manifolds. So for open manifolds. So here we are talking about, just like Victor mentioned a little bit in his talk, cotangent bundles, open unit cotangent bundles, twisted cotangent bundles. These were all open manifolds. And the whole story is actually a very different story than the theorem I wrote or the study of these objects in the closed manifolds. So what happens is that in all of these cases, there is an underlying Floer homological invariant which doesn't vanish, which is non-zero, and this gives you the existence of periodic orbits. This is what's going on. This is, of course, not our case. So Ijani's case is Floer theoretic torsion, some versions of that. And so already at the chain level, it's non-zero, non-empty, so you get non-contractible orbits. Weber's case, I think you look at open unit cotangent bundles and Hamiltonians sufficiently large over the zero section. Again, a little bit similar to some of the things Victor said. And he gets his non-periodic orbits from using the well-known non-trivial fact that the Floer homology for the cotangent bundle, for instance, I don't know, for a quadratic function, is equal to the homology of the loop space. So when you have non-contractible loops, you get non-contractible periodic orbits out of this. So this is, again, a whole different story. Again, in our case, we don't have any of this. So, whereas in this case, the source of the periodic orbits, as I said, an underlying Floer homological invariant. Here, source is which is not zero in these cases. In our case, which is the case of closed manifolds, the source of our orbit is basically presence of one orbit, x. So one non-contractible orbit, and this is our C, then sort of it spawns into many, basically. And the idea of the proof here is because basically there's nothing grows, Floer homology or anything. One has to detect the change through iterations. Okay? So change in filtered Floer homology, that's important. So it should be filtered by a certain action. Maybe I should say, I didn't say it, but I should already. So we understand that the total homology is zero in the non-contractible situation. But of course, this doesn't mean that if you take one orbit and you take it, I mean, if you focus on a little action interval, for instance, a homology filtered homology corresponding to this action window doesn't have to be zero. So one idea in these proofs is that you want to detect the change in filtered Floer homology. So filtered part is very important throughout the iterations. As a result, of course, here we are talking about varying periods, whereas in this case, that's another sort of difference. This is more like topology. Yeah. Mm-hmm. In this case, I did not think, but I don't know. Yeah, let's move this up. So, yeah, okay, so I want to say maybe a few more about other works I said. This board would be a good one for that, but anyway, let's get over here. Under the title Other Works, let me also mention similar things also have been considered for symplectic morphisms. Now I'm back to closed manifolds here by whatever. Okay. So one of the theorems she proves is that for a certain class of monotone symplectic manifolds, closed monotone symplectic manifolds, if you have a Hamiltonian, if you have a symplectomorphism isotopic to identity, and that it has a non-contractible periodic orbit, and that I think it's hyperbolic actually, and that under a condition on its flux, it actually must have infinitely many periodic orbits. So, this is by Botterell. And one more thing let me mention is maybe some of you are familiar with this recent works or recent papers by two groups of people. Here, one is Polterovich and Shelukin, and the other one is Michael Usher and Zhang. So what they do is they study filtered Floer homology in the context of barcode theory or persistent homology techniques. So these ideas actually also at the technical level, the ideas that goes into the proof and what goes in their works are also kind of, there's a lot of resemblance in the methods. Basically, there is also relevant. Okay, so ideas. So far, nobody tried to put the proof of this. I didn't. Of this in the context of barcode theory, but it is possible. I can do it probably. So, that I'm probably writing incorrectly. Okay. So. Okay, so now, next I want to give you a different, so this question is interesting and everything in its own right. We know very little about, from my perspective, it's bad reasons to study it, but there is yet another motivation. At least was my motivation to get into this. And so maybe I'll write it under a little more context that comes from Conley conjecture and ideas coming from that. Okay, so Victor stopped at a very good point. Basically, he brought the whole thing to the examples where Conley conjecture fails. He gave us the irrational rotation, CPN. So these are the manifolds where Conley conjecture fails. So the next thing to look at is, of course, what happens if Conley conjecture fails, basically. So what can we expect? What shall we expect? I'm sure he's going to say more about this, but I'm just going to say, as much as it's relevant to the study of non-contractible periodic orbits, and it's the following thing. Okay, so, but before I get to it, maybe I should also tell you the sort of Frank's theorem. I believe he didn't say this in the morning. So we know the Conley conjecture fails for S2, but we also know the following celebrated theorem of Frank's, also going to 92, which says that, this comes from the Conley conjecture. This theorem says that if you have an area preserving homeomorphism of the sphere, I'll write this here, but it works for homeomorphisms as well, such that it's a set of fixed points. It has fixed points, number of fixed points is greater than 2, then it has infinitely many periodic points. Okay? So this is what happens for S2, basically. Bigger than 2 implies infinitely many. So another thing we know here is that, and this is what Arnold conjecture tells us, which is that 2 is the minimum number of fixed points. So this is the okay. All right, so somewhat inspired by this is the following conjecture. It is inspired by this. So I want to state it this way. I'm not sure. You can call it a principle if you wish, conjecture if you wish. So here's the perspective. So existence of a periodic orbit which is unnecessary from homological or geometric regions. Logical, say, this way, implies existence of infinitely many. Okay. Now, so just take a look at what this says. So in the context of Frank's theorem, you can think about this, yeah. I mean, 2 is the minimum, but 3 is already not necessary, basically. You can think about it this way. Sometimes one can also, and there are versions of this, is that if you have, if the number of fixed points is more than necessary, then you have infinitely many. So this is a more general version of this. So if you have a periodic orbit, which need not be there for whatever geometric or homological reasons, then you may expect to have infinitely many. So now let's go to this theorem, for instance. This is one good example of when this happens. So there is absolutely no reason to have non-contractible periodic orbits. As we said, the Floer homology is 0. But if you have one, which is our unnecessary orbit, to speak, then you get infinitely many. So there are other instances that this is the case. For example, again, I'm sure Victor will say more about this. So if you have hyperbolic, any Hamiltonian diffeomorphism of, say, CPN with a hyperbolic periodic orbit must have infinitely many. Because, again, this need not be there, a hyperbolic orbit in that case. A local version of this theorem also holds that, namely, in this case, you look at, it's a bit different. I'm saying a local version because the manifold is actually the Euclidean space there. So, and specific type of Hamiltonian systems, you have a compactly supported time-dependent perturbations of hyperbolic quadratic forms. And if you happen to have a non-degenerate, say, orbit with a non-zero index, then you can prove that there are infinitely many. Again, in this case, all the homology is concentrated in degree 0, and having something which doesn't have degree 0, non-zero index, having something like that is the unnecessary orbit, so to speak. Okay, so there are instances where this conjecture actually holds, as I said, and that was the original, I should say, the motivation to look at, in my case, non-contractible orbits. Okay, so more. Now, so we are looking, as I said, this phenomenon of one implies infinitely many, so to speak. And this phenomenon actually appears to be, generic. So here's the theorem. Maybe I'll start it like that. In the non-contractible case. So here's the theorem. Again, this is so let's take a free homotopy class again, just as before. Now I want to assume that zeta to the k is not 1 for all k in n. Let's set f sub, not f, I mean zeta here. So this will be the set of Hamiltonian diffeomorphisms of M. M is just a closed manifold here. It doesn't have to be a toroidal or anything. Well, I do need Floer theory, so at least you need the weakly monotone or use virtual cycles or something. But, it's very weak requirement-wise on M. So phi is the set of strongly non-degenerate. So all periodic orbits are non-degenerate, in other words. Hamiltonian diffeomorphisms, and has an orbit in this class. So I'm going to write it this way. Okay. So Mattarella tells us that this set is non-empty. In fact, this set is open in M. So in this, we have the following ones. The ones which have infinitely many. So these are the phis in this curly f sub zeta. The above set, phi has infinitely many simple periodic orbits in classes zeta to the n. So these are basically zeta to the case where k and n, like this. So the statement is that the second set is residual in the first one. Infinity residual. Okay. Again, no assumptions on M other than Floer theory defined and that it's closed. Here is a corollary of this. And the corollary says that actually the set of non-autonomous keys, by which I mean that it cannot be generated by an autonomous Hamiltonian, is infinity residual. Okay, so it is more or less obvious because this set is already residual, and every element here is non-autonomous, because if you iterate autonomous ones, you never get anything isolated, non-degenerate. Okay. So this set is already infinite residual. This is along the lines of actually considerations from the work of Polterovich and Shelikin, I should say. Okay, so now how do you prove something like that? The ideas go back to one of Hinkston's papers and one of our papers. So what you basically do is you use Floer theory to prove this. And the fact that the non-contractible homology, Floer homology, is 0 for in this class. I mean, HF zeta is equal to 0. What you basically show is that if you take a Hamiltonian diffeomorphism here, it must have either infinitely periodic orbits in these classes, which is this case, or that it must have a non-hyperbolic periodic orbit. Now, if whenever you catch in this business a non-hyperbolic periodic orbit, then one quotes the Birkhoff-Lewis-Mozart theorem, which gives you that in the neighborhood of the Hamiltonian diffeomorphism you have actually infinitely many periodic orbits. So you basically go through this. Either in some class you catch something non-hyperbolic and then you are done, or you keep continuing and creating a sequence of non-contractible periodic orbits. This is where this theorem comes from. Okay, so now we need to prove something. Before we get to the proof, however, I want to just say a tiny bit about the Floer homology for this in the non-contractible class. I have to sort of. Okay. Well, zeta is here. Okay. Now, first thing comes first. What I don't want here is that iterations of this homotopy class doesn't become contractible, and that this is not equal to another iteration, let's call it L, if K is not equal to L. Okay? So, notice that if I had torsion, I would immediately have this happening. So, these are important things. The first one is obviously important because, again, we will be looking at Floer homology for iterated Hamiltonians. And if you happen to end up any iterated homotopy classes, so if we end up in a contractible class, this is a totally different ball game, basically. So things won't match up, basically. And this one is important because we basically want to know, when I look at an object like that, say, this is the Hamiltonian sum. Okay. When I look at an object like that, I will know which orbits contribute to this. So it will be important that these guys stay distinct, basically. Okay, so now how do you do this? Again, as I already said, this is briefly the homology of the complex which periodic orbits coming from the class zeta. Here we need a bit more than that. We need an action filtration, as I said, it's important. So let me remind you how the action is defined in this case. So the way it's done is that you fix a action. You fix a reference loop in this class. So fix a reference loop. Let's say Z is here in zeta. Okay. Actually, to be able to talk about any index, you also need a trivialization, although with this thing we won't have much to do with the index, but let me write it here. So a symplectic. This will be the reference to trivialization, or Tn along C. So the action will be, okay, so first of all, what's a capping in this case? A capping is a cylinder in this case. So here is Z, okay, here is X. X is in here too, okay. And then a capping. Normally, when we talk about the Floer homology for contractible orbits, a capping is a disk because the orbit contracts to a point. In this case, the capping is a cylinder. Let's call it gamma. So it's a cylinder or a homotopy. So this will be a map from 0, 1, S1 to M, connecting Z to X. Okay. And now the action will be defined. Maybe I should put a bar here. The integral of your symplectic form over the cylinder plus the integral of H. Okay. All right. So now observe the following thing. What's going to happen if I change this capping, right? So maybe I take a different capping here, something like that. So notice that the discrepancy here will be measured by the integral of omega over the storms, basically. So now, when I assume, again, later on we'll look at the toroidal monotone case, but when I assume that omega is a toroidal, this is well defined, basically. So this is independent of capping. Therefore, I don't actually need the bar here in the toroidal case. If M is a toroidal, W is a toroidal model. All right. So the critical points of this action functional are the objects that we are working. Maybe I'll write here. And the action spectrum are the critical values. Okay, so no, so that's the action. Now, this action is homogeneous with respect to iteration. So k is k times. So I'll write again hk here. K times integral x. Okay, so this is also important. Now the index. So in order to define an index, as I said, one also has to fix in symplectic a reference trivialization along the reference group Z. And then this trivialization extends to a trivialization of the cylinder gamma that we have over there. It gives us a trivialization for x. And then using that trivialization, we can, we can identify the basically tangent spaces along the orbit x, and view them as a symplectic path and talk about indices. So this could be Cohn-Bendit index, of course, and or the mean index, which is, at least in the non-degenerate case, one can think of it as asymptotic Cohn-Bendit index. So index is defined in that way. Now, again, using the coming from the reference one. Okay, now, remember that I'm going to be working with K Hamiltonian sum, iterated Hamiltonians, or iterated Hamiltonian diffeomorphisms, and homotopy classes Z to the K. So in order for things to work, and in order to have this nice properties, for instance, so this will be either the Cohn-Bendit index of an orbit, if x is non-degenerate, or the mean index. Let's write it this way. Victor will say more about these things, I think. So we want this property, for instance, index to behave in this homogeneous way. Now, as I said, things to work out, one has to actually pick a certain trivialization for these iterated orbits. And the way this is done is that for this, when you're discussing these objects, use the, this is important, we use the trivialization which are iterations of the reference one. Of the reference one, and also remember, in each class I have to fix a loop, so I need to fix a loop. Let me write it this way: z to the k. So z to the k, and then use the trivialization which comes from the iterated reference trivialization. And then you will have this property of homogeneous index and all that. Now, of course, you also have filtered Floer homology here. Once you have the action, you can focus on a certain action interval, so you can talk about this. So in this case, we also have this defined for us. So, all right. Let me see if I want to say anything here. Okay, are there any questions? So done with that. So what I want to do maybe is I want to start proving it. And we can do term is stated there nicely, so I can erase this. So I can start, sorry, doing some parts of it. So let's fix the notation. We have a non-contractible orbit there, the x. So let me just, I'm used to zeta now, so let me denote by zeta the free homotopy class of this orbit. And zeta to the k will be by definition this. Okay? And the homology class as before, I'll denote it by the square brackets. All right, so the main ingredients. Ingredients of the proof. One important part is what we call the persistence of local Floer homology. Okay, so here we have, just like in the theorem, we have an isolated periodic orbit. Okay, and let me start with something which is easier. So this orbit, so if I'm going to talk about iterations of it, and if I'm going to talk about local Floer homology, it will be important to know that this orbit stays isolated throughout this iteration. Otherwise, the object won't be defined. So first of all, this stays x to the k is isolated, if x is isolated, under the so-called admissible iterations. I'll tell you in a second what these are. Okay, an admissible iteration, again, going back to Victor's talk, is the following one. An iteration is an integer. K is admissible if lambda, if this is an eigenvalue, so I mean, okay, let me write it this way. Let's do it here. Let's squeeze it here. So K is admissible for a periodic orbit, or let's say for a fixed point H. If lambda to the k is not 1 for all lambda not equal to 1, where for all eigenvalues, so this is an eigenvalue of the linearization dphi Okay, so what we want basically is that if you have roots of unity, we don't want K to be divisible by the degrees of roots of unity among the eigenvalues of the linearization. Okay, so this is what this condition is about. And the essence is literally that if you start with something isolated, it stays isolated. All right. So now what are some admissible iterations? Well, it could happen that all eigenvalues are equal to 1. It's a very degenerate, the so-called totally degenerate case, and then everything is admissible. It may happen that there are no roots of unity among the eigenvalues. Then again, all iterations are admissible for that fixed point. And what will be more important for us is all sufficiently large primes are admissible. Now, here's one of the conditions on how large the prime will be. You want to basically choose it bigger than any of the degrees of the roots of unity if you have them, basically. So this is not the only condition, but this is one of them, definitely. Okay, so now we know when this is going to be isolated, and then we know that this object is going to be defined. Okay. Now, what is this object? Okay, so very briefly, what's happening is that what you do in order to define a local Floer homology of an isolated orbit, first of all, you take an isolated neighborhood of that orbit. And then you want to perturb your Hamiltonian a little bit to a non-degenerate Hamiltonian. And then this orbit will split into a bunch of other orbits. And then if your perturbation is close enough to the original one, and if the support of the difference is small enough, what happens is that the connecting trajectories in this for this new non-degenerate Hamiltonian will all be contained in this neighborhood. Basically, there will be some, action going on, but everything will be in that neighborhood. And then what you do is you quote the standard compactness theorems and the Lewin theorems, which tell you that the broken orbits will also be in this neighborhood. And then you get a Floer complex by just looking at the fixed points one periodic orbits of the perturbed Hamiltonian in this neighborhood, basically. And the differential there will be defined exactly the same way, in the standard way, by counting the number of Floer trajectories between those objects. Okay, so now there is one more step. Of course, you need to do a continuation process, which will tell you that the whole thing, the homology you get, is independent of this perturbation. And then you have something like that defined, basically. There is, of course, stuff to prove here, but I'm just giving you the idea of the whole thing. It actually behaves just like you expect. If it happens to be a non-degenerate orbit, for example, if this is non-degenerate, it's going to be equal to 0. So let's maybe write, I don't know, the homology will be defined over some, let's say, over Z2 for simplicity. If I talk about this will be Z2 if this is equal to the convex Enders index and 0 otherwise. So this is an example. All right, so Once we have this, now I can write the theorem, my item number 1 there that I wanted to write, which is the persistence of local Floer homology. Persistence of local Floer homology tells us that up to a shift of degrees. Okay, so obviously if both of these guys are non-degenerate, the shift will be, in one case you will have the constant index of this one, and here you will have the constant index of this one. So this will be the shift will be the difference. So this result goes back to us. Basically, so this is basically, you don't have to have an aspherical M for this. It also is true if you have cappings in the standard way. The way the proof works, you basically look at two cases, the non-degenerate case, strongly non-degenerate case, and case where you have a totally degenerate orbit, so all eigenvalues equal to 1. And in each case, you see what happens, and you see that this equality, and then the general case follows from the fact that a general system splits into strongly non-degenerate plus a totally degenerate. This is roughly how the proof works. All right. So now, what will be important for our proof? Will be the following fact. If this is non-zero, which isn't, again, here's the statement of our theorem. This will then imply that this is also non-zero, because they are equal, basically. Okay, and this will be the case for all sufficiently large prime. Okay. Now, it's a good moment for me to stop. Is it till 3? Am I speaking till 3? Once. Okay. So because the next thing will be at a different story. So maybe on Wednesday I can start from here. So we assume that we have established one ingredient of the proof. And then we can move on to the other one. So if you have any questions, maybe. Pardon me? No. No, we just started. One ingredient important will be this. I mean, we have some assumptions. We need to use all of them. Yeah, there is more to say.